Hi folks, welcome to chapter 2. In this chapter we're going to be looking at radical and rational functions. Our first lesson today is properties of radical functions. We're going to take a look at some radical functions and see what some of their properties are. So as our first example, we're going to start off by sketching the graph of a linear function, a linear radical function. So let's look at our first example. I've given you a linear function and I want to graph the radical function associated with that linear function. So we start off by basically making a table of values of the function that's given to us, just so we can get a better sense of what's happening to those values. So I'm going to make a table of values here. X, let me pick a different color here. X, the y values are going to be represented by f of x, and then I'm going to have a third column in my table of values, and that's going to represent the square root of f of x. I want to take the square root of each of those functions. That's what a radical is. So let me make a list of points here. By looking at the graph, some of the points I can come up with is 0, negative 2. So when x is 0, f of x is negative 2. I can also take a look at negative 3, 0. When x is negative 3, f of x is 0. I can look at negative 6, 2. So negative 6 and 2. And just to double check, I can also pick some points such as when f of x is 1, f of x is going to be 1 over here, so roughly negative 4.6 and 1. And you'll see in a moment why I picked that specific point. And also pick another point here, say negative 4 and 0.7. These are the points I'm going to work with. In case you're wondering why specifically those points, you will see it in just a moment here. What I want to graph now is the corresponding radical function. So I'm going to take f of x and I'm going to take the square root of f of x and see what happens. So using your calculator, you can go ahead and take the square root of f of x, and what you'll realize is this. For the first part, square root of negative 2 is undefined. Square root of 0 is just 0. Square root of 2 is just approximately 1.4, and in fact I'll change that equal sign to approximately equal to 1.4. Square root of 1 is just 1. And then square root of 0.7 is going to be approximately equal to 0.8. Now, here is one of the reasons why I picked that extra value. What you will notice is that root 0 stayed 0 and square root of 1 stayed square root of 1. These points did not change when I took the square root of them. They're given a special name. They are called invariant points. These are points that do not change. So by definition, these are the points, they remain the same. On both the original graph and the radical graph. Whenever I'm graphing a radical function, I want to always start off by identifying those invariant points. And generally your invariant points are going to be 0 and 1 of the y values of the corresponding function, because square root of 0 is going to stay 0 and square root of 1 is going to stay 1. So let me mark those down. So when f of x y value is 0, right over here, actually let's use a different color so you can see that right here. So that point's going to stay where it is. And secondly, and the reason why I know that's the point is because when x was negative 3, f of x was 0, our new function root f of x is also going to be 0. So when x is negative 3, f of x is 0, square root of f of x also 0. Second point that stayed the same was when x was negative 4.6, roughly here, the y value was 1, and on the new function that's also going to remain 1. So those 2 points are going to remain the same. Okay. Some of the other points I've picked between that region. Now one of the other things I noticed is that anything that was to the right of negative 3 in that region, so this expression here, that became undefined. The reason why it became undefined is because anything that's below the x-axis over there When you take the square root of those numbers, they're negative numbers. They're going to become undefined. So we're going to ignore all these values over here. And the reason why we ignore them is since square root of f of x is undefined for those values, right? Those are all negative values. I'm looking at the y values, by the way. When I take square root of those y values, it's all going to be undefined. So I start my function off from here. That point's going to be on my function on the new graph. I need to fill in the gaps. So the gaps I fill in, I picked a point between the two of them, which was -4. On f of x is 0.7. On the new function, square root of f of x is actually 0.8. It's going to be just above that. So roughly over here. That's going to be the new point. Then I go back over here on the original function, the point -6.2 was there. Now I have the point -6.1.4. So it would be roughly over here. And these are some of the new points I get. I just need to connect the dots and come up with a new function. When I connect the dots, I get the following. This is the graph that I end up getting. One of the things you will notice is that on the new graph, our new function is above the old function between y values 0 to 1, and it's below the new function for y values 1 onwards. So what we say here is the following. When our original function f of x is between 0 and 1, then our square root of f of x is going to be bigger than f of x. So what that means here is, that means, and I'll highlight it over here, when our original function f of x is between y values of 0 and 1, right here, then for that region our new function is going to be above that function. And then the moment I look at the original function above y value of 1, so over here in this region, then the new function will end up being below that function, right? So that's what that expression is basically suggesting. And I'll formalize the rest of it. So when it's between 0 and 1, root f of x is bigger than f of x. When f of x, original function, is bigger than 1, then square root of f of x is going to be less than f of x. And then lastly, one of the things that we notice is that when f of x is equal to 0, or f of x is equal to 1, then square root of f of x was also equal to 0, and square root of f of x was also equal to 1. And then these were the invariant points. So the process that we're going to be using to graph a radical function is, we're going to start off by making a table of values of some of the points that are given to us. We're going to identify the invariant points. We're going to graph the invariant points. And we're going to pick some values in between to try and see what's happening to our new function. Okay? Let's give that a try in our next example. I'll give you a moment to give our next example a try. You can pause the video, give it a try, and then come back and we can check our work. So once you've had a chance to try it, this is the way I would like to set it up. Here are the steps I'm going to follow. I'm going to start off by marking some of the invariant points. Once I figured out what the invariant points are, I'm going to write those down. Those points are going to remain the same on both the original graph and my new graph. My second step is going to be pick some other points that are on this original graph and then transform them by taking the square root of those, and then see what they end up looking like. And the final step is going to be completing the graph by connecting the dots. Okay, so let's see what our invariant points are first of all. Our invariant points are always going to happen where the y values are 0 and 1 on the original graph. So the first invariant point I'm going to have is right here because the y value is 0. And here the y value is 1. So those are the two invariant points I'm going to have, and I'm going to make a note of that. Okay, invariant points. Once you have identified those invariant points, now we can pick some other points that are going to help us complete that graph. So some of the points we can pick are the ones that are actually given to us. Those are nice numbers to work with. So one of the points we're given is x is 0, f of x is 3, so I can try that, 0 and 3. The other point given to me is x is 4 and f of x is 9. So 4 and 9. And I can pick a point in between these two invariant points just to kind of give me an idea of what's happening. So a point in between those invariant points could be an x value of negative 1.5. And if I take a look at my original graph, an x value is negative 1.5, so roughly over here. I have a y value that's going to be sort of over here, and that point is roughly, I would say, 0.5 or 0.6. So I can make a note of that, negative 1.5 and 0.6. So these are the three values I'm going to work with, and let's see what I get. X is 0, f of x is 3, square root of f of x is root 3, which gives me approximately 1.7. X is 4, f of x is 9, root 9 is going to give me equal to 3. And then lastly, when x was negative 1.5, f of x was 0.5, square root of 0.6, is going to equal 0.7. So the new points are going to have the same x value as before, but the new y value. So when x is 0, I have a point at approximately 1.7. X is 0, 1.7 will be roughly over here. X is 4, a new point is going to happen at 3. I'll have a point right here. X is negative 1.5, the y value is going to be at 0.7, so 1.5 is going to be just above that point over here. Okay, let's try that one more time. So now what's going to happen when you connect the dots, you're going to see that between 0 and 1 y values, your new graph is going to be above the old graph, and as soon as you cross that, it's going to start connecting below the original graph. So you're going to get a shape that looks like this. And that's one of the common properties of a radical function. Between 0 and 1, when you take square root of numbers between 0 and 1 that are decimal, the end result is a bigger decimal, or a bigger number. And when you take square root of numbers that are bigger than 1, then the end result is a smaller number. And that's why the graph is behaving this way. Perfect. Let's try another example. This time we're going to take a look at a quadratic function. See what happens when we take the square root of a quadratic function. Our steps this time are going to remain the same. The process is exactly the same, only the resulting graph is going to look a bit different. So let's take a look at what we're working with. Again, our first step was to mark the invariant points. Let's go ahead and do that. So step 1, mark invariant points. Now, by the way, in this example, I'm working with an upside down parabola, so you should know this is a negative x squared function of some sort. So invariant points are again going to happen where the y values are 0 and 1 on the original graph. So here's going to be an invariant point here, an invariant point here, an invariant point here, and an invariant point here. Those four are the invariant points. The next step is make a table of values, pick some points. So I'm going to make a triple table of values with x, f of x, and square root of f of x on this table of values. So let me go ahead and fill those numbers in. Some of the numbers that are given to me to work with are this point here, negative 1 and 5. Another one that I've got to work with is 0 and 8, 1 and 9. And then lastly, I've got 3 and 5 as well. Actually, we've got one more. We've got 2 and 8, 3 and 5. Those are some of the points that are given to us, and we'll see what happens if we pick those points. Okay, so x is negative 1, f of x is 5, which means square root of f of x is going to approximately equal 2.2. 8 square root of 8 is going to approximately equal to 2.8. Root 9 is going to exactly equal 3. Root 8 is again going to approximately equal 2.8. And lastly, root 5 is going to approximately equal 2.2. This time I can pick some more points if I want to, but I've been given a good spread of points to work with, so I should get a general shape that makes sense. Now, using these points and the common concept that whenever I'm working with points between 0 and 1, my square root function is going to be above that original function, and after that it's going to be below, I can complete the graph. Let me go ahead and plot these points first. X is -1, f of x is 2.2. X is -1, f of x is 2.2. So my new point is going to be here. X is 0, f of x is 2.8. X is 0, f of x is 2.8. X is 1, point is 3. X is 2, 2.8, 3, 2.2, 2, 2.8, 3, 2.2 again. And now I can complete the graph. Whenever I'm between 0 and 1, my new graph is going to be above that. As soon as I cross over, it's going to be below that. Connect the dots. Keep connecting the dots, and again, same part. Okay, that didn't work out very well. Let's try that again. Keep connecting the dots, and you're going to get this graph right here. Now it's really hard to see over here, but the new graph is definitely above the old graph between 0 and 1. So that's the shape that you're going to end up getting. We can finish solving the problem. The next part that we need is we want to state the domain and range of our new function. So looking at our new function, we can say domain and range of square root of f of x are going to be, so the domain. Now I know that this particular function is continued on in this direction and in this direction, but for x value bigger than 3 and x value less than -2, sorry, x value bigger than 4 and x value less than -2, my new function is going to be undefined because the y values are negative here and negative here. So I'm going to ignore anything beyond those points. I'm only going to look at the x values between -2 and 4 because that's where my function is defined. So as a result, the domain is going to be x is bigger than or equal to -2 and less than or equal to 4. Similarly, for the range part of it, my new function is going to have a range from 0 all the way up to 3. So the range of this new function is going to be y is bigger than or equal to 0, less than or equal to 3. And again, that's the key idea, is to make sure that the domain is properly classified. In my new function, the domain was all real numbers because the graph continued on, but here I got to recognize that here and here my new function is going to be undefined. I'll be taking a square root of a negative y value, which is not allowed. Same idea, try the next example. We will compare our answers in a brief moment. Pause the video and give that a try. Let's see what you came up with. The steps are exactly the same. I'm going to start off by marking down the invariant points. The invariant points happen wherever the y value is 0 and 1 on the new graph. The y value is 0 and 1. So here the y value is 0, 1, 0, and 1. Those are the invariant points. Okay. Next, I'm going to pick some key points to test. So the points I picked were already the ones that were given to me. Those values right here. So when x is -6, f of x is 6, square root of f of x is 2.4. So I'm going to get, when x is -6, new point at 2.4 roughly here. When x is 2, f of x is 6, new point at 2.4 again. So when x is 2, f of x is 6, square root of f of x is roughly 2.4 over here. And then just to show you something, I picked a point in the middle here, -2. When x is -2, the y value, or f of x, is -2. When I take the square root of that, it's actually going to be undefined. In fact, this entire region is going to result in undefined values. Because the y values there are all negative, and then we're taking the square root of all those y values. So that entire region is going to be undefined. Once I have those points, I can complete the graph. I know between 0 and 1, my new function is going to be above the old function. And as soon as I cross over, it's going to be below. So I'm going to get this graph right here, albeit a bit smooth than what my tablet is letting me do here, so let's give that another try. Third try. It's very sensitive to touch. Hopefully okay, that's a little bit more manageable. Do the same thing on this side. Between 0 and 1 it's going to be above, after that it's going to be below, so it's going to look something like this. Right, and again you can check some more values to see how is it going upwards or is it going towards the side. You can take a few more values, but based on the points given to us, that's what the general shape is going to look like of our new graph. It's going to be a piecewise function which is basically valid from this point onwards and valid from this point onwards in that direction. Okay. Next, let's take a look at the domain and the range. For our original function, the domain and range of our graph, was domain is all real numbers. It's a parabola. The range was y is bigger than or equal to -2. That was the original function. For our new transformed function, which is square root of f of x, our domain is going to be all values bigger than that number, so all values bigger than 0, and all values less than that number, so all values less than -4. So when I write that out, my new domain is going to be x is bigger than or equal to 0 and x is less than or equal to -4. It's a piecewise function. Similarly, the y values, if I look at all possible y values, my new function is going to have y values bigger than 0, right? So that's going to be the new range. Y is bigger than or equal to 0. So those are some of the key properties of radical functions. Regardless of what original function is, some behaviors are going to be very similar. Let's take a look at what happens when we take the square root of a cubic function. That's our next example. Here I've given you a cubic function. I've given you some key points to work with, so you're not estimating. Same process. Let's start off by identifying the invariant points. So our invariant points are going to happen wherever y value is 0 and y value is 1. So I have an invariant point here, I have an invariant point here, and I have an invariant point here. Okay, that's where y values are 0 and 1. Next step is I want to pick some key values, so I'll make a table of values, x, f of x, square root of f of x. Some of the key points I'll pick are basically the ones given to me. I know when x is -0.5, f of x is 0.325. When x is 2, f of x is 6. And I think those 2 points should be enough to give me an indication. Actually, I missed an invariant point. I also have an invariant point over here. There's another 0 over there. Okay, so invariant points are done. Couple of values we picked. Square root of f of x is square root of 0.325. I get approximately 0.6. And square root of 6, I get approximately equal to 2.4. Let me graph these points. So at -0.5, I'm going to have a value that's roughly 0.6, so above that. And at 2, I'm going to have a value that is 2.4, so here. Now I know wherever the y values of the original function are negative, my function is undefined. So here it's going to be undefined. I'm going to lose that part. Between 0 and 1, my new function is above the old function, so I'm going to get a bubble that looks like this. Nothing in that region, nothing in this region, it's undefined region, right? That's where it's going to be undefined. And then again, between 0 and 1, it's going to be above that function. And as soon as I pass that, it's going to be below. And it's really tricky to kind of sometimes connect this graph, because if I do it too closely, you won't see the difference. This is what's really happening, right? You're above that function and below after you cross the invariant point of 1. So that's all it really is. You know, we're understanding the behavior of radical functions. One final step, let's identify the domain and range of our new function. So for square root of f of x, our new domain is going to be, now we have a piecewise domain. Our new domain is going to be x is bigger than or equal to -1 and less than or equal to 0. It's valid there. and x is bigger than or equal to 1, it's valid in that region. And for the range, y is bigger than or equal to 0. Right? I know y is between 0 and 0.6 in this region right here, but in this region it's all real numbers bigger than 0, so that kind of takes over the overall range. Okay, that brings us to the end of this problem. We're going to finish off our lesson by using our graphing calculator to also examine some basic properties of radical functions. So our next example is just that. This time I've given you a radical equation. It's an equation with the radical function in it. And we're going to learn how to use a graphing calculator to solve for that radical equation. Okay, so take out your graphing calculators, reset it, and then we will take a look at this problem. So once you've got your graphing calculators ready, what we need to do next is graph that equation and try and find its solutions. Two ways we can do that. One way is we can rewrite the equation and bring everything over to one side. So let me do that first. So I can rewrite that as square root of 2x minus 1 minus x plus 4 equals 0. And then I can simply graph this left hand side and look for its intercepts. Okay, so I'm going to graph y equals that function, square root of 2x minus 1 minus an x plus 4, and look for intercepts. Another way I can do this is I can go ahead and graph the left hand side and the right hand side separately and also look for the intersection points. You can plug that in as y1, y2, and look for the intersection. I prefer this method because then you're not playing too much with the window settings. You're only going to be worrying about the x values, and the y value is just going to be in the range of, you know, -1 to 1 because you're looking for the 0. Let's go ahead, plug this into our calculator. Okay, y equals square root of 2x minus 1, bracket close, minus an x plus 4. We graph it. We get a function like this. We're looking to see when this function is going to hit 0. Those are the x-intercepts. We'll notice that the function is going to hit 0. Oops, let me bring that back up. It's going to hit 0 right about over here. Right, so I can adjust window settings to get a better look at it. I can go to the window settings. I can make my x minimum 0, make my x maximum a bigger number, say 15, and I can make my y minimum a -2 and y maximum a +2, just so I get a nicer look at the intercept. Now when I create the graph, I'm going to get that graph right here. This is the point that I am looking for right here. Okay, that point is the intercept. You all know how to trace that. Let's go ahead and do that. So we go second, trace 0. You want the left bound, go to the left of that graph, press enter. We want the right bound, go to the right of that intercept, press enter. And then your intercept's going to be in between those two triangles. And then press enter for the third time, and the calculator is going to tell you what the x-intercept is. And in this case, when y is 0, the x value ends up being 7.8284. We'll round to the nearest tenth. That's what the question is asking for. So we'll say x value is approximately 7.8. So x is approximately 7.8. And now you know how to use your graphing calculator. That brings us to the end of this lesson. Thank you for watching. You can go ahead and try the problems assigned to you in your homework.